Let me share my screen and get it up. There we go. Oh wait, I forgot to do it with sound. There. Now, hopefully this will work. This is the Harrow-Hasidim-Lloyd algorithm, or the HHL, and it's by Christopher Gilbert, Aditya Bastola, and Tony Chen, the block beavers. So, quantum mechanics describes how extremely tiny particles behave. They don't act like regular objects, but according to probabilistic laws. Because of these probabilistic laws, quantum particles can be in more than one state and in more than one position at the same time. Regular computers store information with ones and zeros, which is called a bit of information. Quantum computers store probabilities of 0 and 1, which is called a qubit of quantum information. Because qubits are probabilistic, they can be in more than one state at once, and therefore can compute more than one thing at the same time. This parallelization allows quantum computers to do much more than regular computers. The HHL algorithm solves a system of linear equations, which can be written like the thing on the left, with a solution y equals 3/8 and z equals 9/8. But it can also be rewritten as the product of a matrix and a vector being equal to a vector. And generally, any system of linear equations can be written as ax equals b, and can be solved by just multiplying b by the inverse of a. In order to find the inverse of a, you need to find what's known as its eigenvectors and eigenvalues. So an eigenvector is any vector v such that when it's multiplied by a, its result is just scaled up by some amount, and that amount is called the eigenvalue. So by finding v and the reciprocal of the eigenvalue, you can find the inverse of the matrix, and you can therefore solve the system.
Before we can actually perform computation on our inputs, we have to encode our inputs into quantum registers. We encode vector b using amplitude encoding, where the elements of vector b are normalized such that they can be represented as the amplitudes in a quantum state. We need to normalize the elements of vector b because the elements of vector b can be much greater than 1, and in a quantum state, the sum of the squares of the amplitudes must equal to 1. Using the QPE algorithm, we encoded the eigenvalues of A using basis encoding, where a register can be read as a bit string. Then we perform controlled rotations based on the matrix A's inverse eigenvalue to entangle an extra qubit. We do this so that in the final state, when we actually measure the ancilla qubit, we can tell if the entangled solution is actually the desired solution. If the 0 state is measured, the entire process is repeated until the 1 state is measured. Then we invert the QPE so that we can express the solution in terms of an understandable measuring basis. In other words, in terms of the 0 state or the 1 state, rather than the eigenvector basis, which the original QPE put the register in.
Results. The final state of the register contains the amplitude encodings of the system solutions. To get results, we repeatedly measure the system and find the ratio between measuring each state and when the one state from the second to last slide is measured, as we can see from the picture. To get the amplitudes from the results, we take the square root of the ratio, so the ratio between the solutions is 1 to 3. This means that our algorithm was correct, as z 9 out of 8 is 3 times y 3 out of 8. Challenges. Some of our challenges were finding the right difficulty for the paper, and after changing our paper twice, we had another hurdle to cross: understanding the various components of the paper, implementing them, and putting the various code fragments together. And keep in mind that none of us have ever taken a linear algebra class, so asking for help and learning from TAs and instructors when we needed it was crucial for us to finish this project on time. And also, why should you care? The major drawback of HHL is that it requires more qubits than most other quantum algorithms, which is a big problem when considering that only big companies have access to a large number of qubits at the moment. However, it is extremely fast, only O of log n time, and is also very useful. HHL is multifaceted. This means that it has many use cases across sectors of society, such as machine learning, cryptography, graph theory, etc. Thank you for listening.
And then I also have a video of it actually running on 10,000 iterations with 5 qubits. And I've sped it up quite a bit because it takes a while to run. But basically, the more iterations you can do, the more accurate it gets. And the more qubits you add, the more accurate it gets as well. So we couldn't get the resource estimator working, but this version of the in the optimal case, our algorithm uses 5 qubits, but the more qubits you add, the more accurate it can be. And here we see it outputs the solution of 3/8 times the vector 1, 3, which is our solution. So I think we're good for questions. Oh, also time complexity. The best case for classical algorithm to do this is O of n squared, and ours is O of log n. So this method of doing it is way faster than classical algorithms. Okay, now for questions.
Wait, I have a question. Why'd you guys end up changing papers in the middle of the project?
So I think we originally started with something called the regularized least squared solver problem, but within that paper, it kind of just used the HHL as a subcomponent and was just like, oh, and we implemented the HHL in order to do this. So it was like our original paper had this entire other project kind of built within it. So when we found that out, we found that it was like going to be way too hard and way too much kind of work to implement all of it. So we ended up just going for that kind of smaller subcomponent of the HHL.
Also, like we were given another paper that was like HHL, but like a really like small like the paper describes solving like tridiagonal like matrices, which is like no one uses that, so there's kind of no point in like implementing that.
Yeah, so we chose to do the full HHL. Any other questions?
What are the typical use cases of HHL?
Pretty much everywhere that either a linear system of equations needs to be solved or the inverse of a matrix needs to be found.
You can
And for
use
the
it.
matrix,
Oh, sorry, but you can like
that's fine.
Yeah, there's like the least squares problem, which are like the one we were originally doing, but like that's like linear regression.
Yeah, and then in the slides, it also said like machine learning and financial analysis. And probably with finding like inverse of matrices, because that's what this algorithm is essentially doing. It's, I'm guessing, probably also very good with like linear algebra and solving those types of problems. Okay. Any other questions?
If there aren't any more questions, we can move on to the entanglement investigators. I'd like to say that I'm really proud of the work that you guys put in for the HHL algorithm and having to go through like switching to paper